Hello everyone, this is topic 0.3, sequences, the last tool necessary to be able to understand our main goal, which is series. And so we're going to go through this rather quickly here. We say that, we define a sequence as a function whose domain is the set of positive integers. And we say that there's a mapping from the set of positive integers to the terms of the sequence. So, for example, instead of using x, we're going to use a, and we might have the first term, or excuse me, we're going to have the domain be just the set of the positive integers. So the domain is just the numbers 1, 2, 3, 4, and so on. Now, we don't say the term infinite, but we mean an infinite sequence. And then we basically just send those elements that are in the domain through the defining nth term of the sequence, because way out here is like what we call a sub n. I'm sorry, this goes to infinity, so okay, we send 1 through the defining equation for the sequence to get the range, which would be a sub 1, the first term of the sequence. Then you send 2 through there, you get a sub 2, send 3, and we'll see exactly what we mean in a moment. Into the defining nth term of the sequence, you get a sub 3, a sub 4, and so on. And there's some nth value in the domain, and that produces the nth term of the sequence, a sub n. So we could denote a sequence either by, as we see in this example, defining what a sub n is, so 1 over 2 to the n in this case, or you could put it in braces like this, so it could be written as 1 over 2 to the n. So the braces are used exclusively for the notation of a sequence. So keep that in mind when we write out our general theorems. So this is just saying write the first 5 terms of the sequence and make a graph. So the domain, don't make this harder than it is, because it is this simple. The domain is just 1 through 5 for this case, but we do know, of course, that it goes on forever. So the range, just plug these values in for n in the defining equation a sub n. So the first term a sub 1, 1 over 2 to the first. Second term a sub 2, 1 over 2 squared. You don't have to call them a sub 1, a sub 2, it's just what they are, but these are the numerical values. When n is 3, 1 over 2 cubed, and so on. 1 over 2 to the 4th, and 1 over 2 to the 5th, etc. Probably want to evaluate those 1/2, 1/4, 1/8, 1/16, 1 over 32, and so on. What a sequence is, really, all that it is a list of terms, a list of numbers following a pattern that is dictated by the defining equation for the nth term. Okay, so that's all that a sequence is. And we're not going to play the Jeopardy game where I give you a list of numbers and then you tell me what the sequence is. We're just going to go with the fact that if I want you to write out the terms, you just write out the terms, plugging in the domain, which again is the set of positive integers. And so if we were to graph this, the axes change. The horizontal axis, which is typically our x-axis, is now labeled as n. n meaning the set of positive integers. And the vertical axis is labeled as a sub n. Now, the highest this gets is 1/2, so let me say that's 1/2. And I'll say this is 1/4. And let's just plot the points. When n is 1, it's 1/2. When n is 2, it's 1/4. When n is 3, it's 1/8. I won't want to put that in there, I guess that's fine. When n is 4, it's 1/16. When n is 5, it's 1/32, and so on. That's what a sequence is. This is discrete in nature. And by discrete, we mean it's not a continuous function. We're not joining these points. It only exists, the sequence only exists at the set of positive integers, and these are the respective values of that sequence given in this list, and there's your graph. Now, a couple things that we'll probably abuse more than we ever will even think of the fact that we're using them is the following definition and theorem. We first define the limit of a sequence. And we say the limit as n goes to infinity of a sub n equals L, and that's the limit. And if sequences have limits, they converge. If they do not have limits, they diverge. And then this theorem bridges the gap between the discrete nature of a sequence and the continuous nature of a function. Because what it's saying here is you have the limit as x goes to infinity of a continuous function f of x equaling L. So this is continuous. And then you have a sequence such that, here's a key point, the continuous function matches the discrete function. See, this is a discrete limit here because it's talking about n and a sub n, and it only exists at those values. But this is a very powerful theorem because what it's saying is that these are the same. The continuous and the discrete produce that same limit as long as there's this condition where the function at n matches. And really, now what that does, what this portion does, is it really takes your graph and it makes a function out of it. So here's the function f of n equaling 1/2 to the n in this case. So the whole point here is this. What the definition and the theorem allow us to do is use our limit laws. Limit laws for sequences are analogous to limit laws for functions. So it allows us to use L'Hopital's rule and all of the limit rules that we've established. So if you have to determine if a sequence converges or diverges, you basically just take the limit, because if the limit exists, it converges. If the limit does not exist, it diverges. So here, we'll just take the limit as n goes to infinity of a sub n. That'll be the limit as n goes to infinity of n squared plus 1 over 2n squared plus 1. And this limit, recall we studied this, we saw an example earlier where this is the special case where if the, well, let me show it in two ways. We'll first do L'Hopital's rule, because a direct substitution gives us infinity over infinity. So by L'Hopital's rule, we get the limit as n goes to infinity, I put the little L error above there, of 2n over 4n squared. And we can cancel out the 2n, That's 2n over 4n to the first, I'm sorry. We can cancel out the common factor of 2n, and we get 1/2, and the limit of a constant is a constant, so the limit is 1/2. Now remember the special case? This is the special case that from now on, we're going to use this every time, so make sure you know that this is special in terms of the evaluation of the limit. That is, if you have the limit as the variable increases to infinity of a ratio of two polynomials where the degrees of those polynomials are equal, in this case degrees are 2, then the limit is just going to be the ratio of the leading coefficients. So in this case, 1 over 2. Okay, so in the future, we're going to use that rule, that special rule, and we're not going to go through the L'Hopital's rule. So just use that special case. Let me just show you this, though. This is, let's say for fun, let's write out some of the terms. And we can do this off to the side. If I put a 1 in here for n, that'd be 1 squared plus 1 or 2 over 1 squared is 1 times 2, 2 plus 1 is 3. That's the first term. The second term is going to be when n is 2. So this can be 4 plus 1 or 5 over 4 times 2 is 8 plus 1 is 9. Next term is going to be when n is 3, so that's 3 squared is 9 plus 1 is 10 over 3 squared is 9 times 2 is 18 plus 1 is 19. Let's just do a couple more. When n is 4, 16 plus 1, 17 over 16 times 2, 32 plus 1, 33. And one more. 25, when n is 5, 25 plus 1, 26 over 25 times 2, 50 plus 1, 51. Those are the terms of the sequence. And notice as we go further and further out, they're approaching 1/2, which was the limit of that sequence. Okay, so kind of interesting to note that. Okay, for this example, so that's the limit of that sequence. Okay, for this example, it's kind of a funny one, because if you try direct substitution, well, first off, you're going to take the limit as n goes to infinity of a sub n, which is the limit as n goes to infinity of 1 plus negative 1 to the nth. If we try direct substitution, it's kind of funny looking because you get 1 plus negative 1 to the infinity. And that's kind of weird because, here, I'm going to just box that off to the side. That's kind of weird because really, what does negative 1 to the infinity mean? I mean, if infinity is odd, that means negative 1. If infinity is even, that means it's positive 1. So this is not really understandable. So what we're going to do is we're going to write out the terms. So if you ever get stuck and you can't evaluate by our limit properties, just investigate the behavior by writing out the terms. When n is 1, okay, we'd get 1 plus negative 1 to the first. When n is 2, 1 plus negative 1 squared. When n is 3, 1 plus negative 1 cubed. 1 in is 4. 1 plus -1 to the 4th. Usually the first 4 or 5 terms are going to be more than enough to notice a pattern. Okay, and then let's see. If the power is odd, it's -1, so 1 plus -1 is 0. The power is even, it's +1, so -1 squared is 1, plus 1 is 2. -1 cubed plus 1 is 0. -1 to the 4th plus 1 is 2. -1 to the 5th plus 1 is 0. And basically this is just a pattern of 0s and 2s, right? It's bouncing back and forth. And with regards to the limit, okay, because that's the whole idea. If it has a limit, it converges. But sequences that do not have limits diverge. And this limit, this is not tending toward anything. It's just bouncing all over the place. So therefore, the limit does not exist. Call from Calculus 1, we use DNE, right? So then we would say that it diverges. But it doesn't diverge because it approaches infinity. It diverges because it has that kind of silly behavior of bouncing back and forth between 0 and 2. And if you wanted to, you could even graph this to kind of visualize the fact that there is no limit. The limit does not exist, because if this is n, if this is a sub n, okay, when n is 1, it was 0, and then it just started bouncing back and forth. When n is 2, it's 2, and it's 3, it's 0, 4 back up to 2, 5 back down to 0, and you can see as well on the graph that the limit does not exist. Okay, so that's it for sequences. We're ready to start series, and we'll see you when you're ready.